Welcome back. What you're about to hear is the lecture for Week 3 Laboratory. We are going to be adding some extra topics in this, so make sure you take careful notes. The topics that we're going to cover is we're going to go over some of the basic energy audit types, equipment and data collection, the energy audit report itself, and then we're going to go over the semester project overview, something that you're going to be doing every week from here on out. The first thing I want to talk about are energy audit types. And most of the time, energy audits are divided into three main categories. And the categories are based on the amount of time is spent on doing the audit, which actually in the end result relates to how much money. So the first or most basic type of audit is called a walkthrough audit. In general, this means that you're going to walk through the building and look for probably the most obvious of things. The hallmark of this audit is we don't take any time to sit down and do any type of calculation. So the audit takes the least amount of time and the least amount of money. It also provides no real in-depth analysis of what's going on. A lot of times a walkthrough audit will be used to decide if more money should be spent on a more elaborate audit. The second tier of audits are called a mini audit. And like should be already figured out, this is going to require more time and cost more. In this audit, the hallmark is we're going to start doing some basic calculations and taking some basic measurements in the field. So we're going to spend a little more time. We're going to start taking a little closer look at some of the different areas. We may bring some basic tools. We may measure some things. And we're going to do some simple hand calculations. The final audit, which is the most elaborate of the audits, which takes the greatest amount of time and the greatest amount of money, is called a technical assist audit or full energy audit. The hallmark of this audit is typically we recreate the building in a computer. So we use some sort of computer load calculation and simulation program like Carrier HAP program or Train Trace, and we recreate the building in a computer simulation. What this does, it allows us to actually compare existing equipment to see if it's oversized, undersized, whatever, and we can put in the utility bills to get a theoretical cost of operation. Now, the objective in a technical assist audit is to develop a computer simulation that's accurate enough where we can actually mimic within a plus or minus 10% the actual utility bills throughout the year. I know to be acceptable by the federal government, we have to be able to match within 10% one summer bill and one winter bill. That's acceptable if we're doing an energy audit for the federal government. Now, once we have that, we can start using the computer simulation to do what-ifs. What if I add a higher efficiency furnace? What if I add a higher efficiency rooftop unit? What if I add insulation to a roof? What if I do combinations of things? How does one energy conservation measure impact another? A computer simulation allows that. Now, a little bit of background. The federal government coined the previous audit terms in the first National Energy Act of 1978. Those terms have pretty much been used over time with minor changes. Now, in recent years, ASHRAE, the American Society of Heating, Refrigeration, Air Conditioning Engineers, has also defined levels of audit. And they correspond roughly to the levels you just heard. So a walkthrough audit, or the simplest audit, is an ASHRAE level 1. The mini audit, which we're going to do a little more work, spend a little more money, is an ASHRAE level 2. And the full technical assist audit is an ASHRAE level 3. Now, it should be important to realize that ASHRAE also identifies something called a pre-audit. This is something that you've already done, especially during the first week's lab. The first week's lab, you generated an energy utilization index. So you took some utility bills, you came up with a baseline. ASHRAE calls this a pre-audit. So ASHRAE, before you even get into the audits, will take the utility bills and generate an energy utilization index, which is why we started at that point. Now, it's important to note that as of this year, and it's 2016, ASHRAE will be coming out with an energy audit standard. So stay tuned. They're going to actually try to hammer down specifically what's in an audit. And possibly this might be adopted by various levels of government, whatever. So stay tuned. The next thing we're going to talk a little bit about is energy audit equipment. Some of the equipment should be obvious. When you go out in the field, flashlights are always important. Screwdrivers, nut drivers, so you can actually access and take a look at equipment. Tape measure, so measurements, footprints can be taken. Simple sonic or laser tape measures are valuable. The sonic and the laser come in real handy for measuring ceiling heights, especially high ceiling heights. Now, another piece of equipment that I don't have listed here that comes in real handy is a simple compass. A lot of times you get in a building, the building isn't exactly square, and you get into rooms, and it's still important to understand what the orientation of the rooms are. This is where a compass comes in handy. Under advanced equipment, it's always nice bringing a multimeter to check voltages, amp draws on things. A side note under a multimeter would be some sort of simple watt meter that you can plug in and actually plug small pieces of equipment in to get an idea of what kind of wattage they use. That's always handy. A temperature, humidity, CO2 meter of some type is handy. CO2 is good to decide if ventilation intake is adequate. Temperature and humidity also important, so we know if they're within the proper tolerances for the type of space that we have. And then finally, thermal imaging camera. In recent years, the pricing on these have come down considerably. You can now get thermal imaging cameras that actually pop into the bottom of your smartphone. They run about $300. These come in very handy to look at windows, doors, walls, check for differential temperatures happening in places. You can even detect moisture getting in under different areas. You can look at electrical boxes and see hot spots. Thermal imaging cameras really become a valuable tool in doing energy audits. The next thing that's important to have before going out and starting an energy audit is a set of blueprints, hard copy or electronic, and then a set of building footprints in a small version, such as egress maps or maps that are used in the building to understand how to leave the building when there's a fire. These smaller footprints are excellent to use when going out and collecting data on site. What I want to take a second to go out and look at some egress building footprints. This is an example of an egress building footprint. This happens to be Artworks here in Big Rapids, Michigan. These set of footprints are going to end up becoming very, very familiar to all of you this semester because this is going to be your semester project. So the key ingredients to a good footprint is having hopefully a current layout that shows all the different walls, and most importantly is the orientation. So do I know how the building is oriented? And this particular footprint fits the bill nicely. And as you remember, you should have covered this in your 342 class, the proper way to collect data. It's probably one of the most crucial things in an energy audit is having detailed data collection. The worst thing that can happen in an audit is missed data. It causes increased cost, it lengthens the time of the data, or the time that it's going to take the energy audit to be done, and it frequently puts the customer out. The customer sometimes has to bring in somebody special to get you into different rooms. They may have to set up a special time to get you in after hours. When you finally get access to all the different spaces, it's critical that you make the most of going out and collecting data. So what we're going to do is take a quick look at the data sheet that you guys should already be familiar with from your load calculation class. Now, this data collection sheet should look relatively familiar. Basically, on the top, it has the name of the building you're working on. Under space name, it gives the space name and possibly what its function is. And then under space number, in this case, it gives you a level identifier and the specific room identifier. Within this space down here is where somebody will take the time to field draw the building. In this case, somebody had a set of blueprints ahead of time and simply used a screen capture and snapped the basic footprint onto the data collection sheet ahead of time. This is also very handy. You'll notice that they took the ceiling height. Somebody already calculated an area from a set of blueprints, which is also very handy. There's an orientation on here, so we know what north is. This happens to be a basement level, so we know there's no exterior walls. This is not a walkout type building. The A's and the B's on here are showing two different lighting types, which are described on the next page. And it's also showing the position of a thermostat. On the next page, there's an area at the top to indicate windows, and because this is below grade, there are no windows. But if there were, you put the window identifier, typically a WA, WB, etc., the height, then the width, and then the pane explanation. What size pane glass, what type of gap, and then what type of pane. So a typical commercial building would have 1/4 inch thick glass, 1/2 inch gap, and another 1/4 inch pane. That would be for a double pane window. Is there any unique type of film on the window? Yes or no, like a reflective or insulating film? Is the window operable? In other words, can you open the window? Yes or no. What's the frame construction or type? Aluminum, wood, steel, what is it? Is there a thermal break? So if it's aluminum or some sort of metal frame window, did they put a non-conductive material to break that metal between the inside and outside? You typically can see it if you look in between the panes of glass at the frame. Is there internal shading? Blinds, drapery, is there something that the customer or the building owner can use to block out solar? And then finally, is there external shading? So are there buildings, trees, overhangs, awnings? Is there something outside that would also help eliminate or minimize the amount of solar transmission? Under the lamping, typically we identify in each room the different types of lamps and the quantity or fixtures. Then we also give fixture type. P stands for pendulum or free hanging. In other words, the light is actually hanging out into a room. R stands for recessed. In other words, it's flush with the ceiling. And surface mount means it's not up into the ceiling, but it's mounted to the ceiling. Under lamp type, I is incandescent type lamp, F is fluorescent, HID is high intensity discharge, like mercury vapor, metal halide, or high or low pressure sodium. And then LED is self-explanatory. We have the number of lamps per fixture, the wattage per lamp, and then a lamp itself descriptor. Now, under fluorescent lamps, typically we have the type of lamp it is, followed by the length. So the T stands for tubular, the 12 stands for the diameter in 1/8 inch increments. So a T12 is 12 1/8 of an inch in diameter, or 1.5 inches. The foot 4 stands for a 4-foot length. Ballast type, we have magnetic, we have hybrid, and we have electronic. Most of the older fluorescents, especially the T12s, you could still find some magnetic ballast out here. All the current or newer fluorescents use electronic. There was only a small window in the late 80s, early 90s where hybrid ballasts were used. Finally, the ballast factor. The ballast factor is how much more energy the ballast adds to the actual wattage of the lamps. So after you tally up all the wattage of the lamps in the fixture, you have to multiply by that factor to get the total wattage used by that fixture as a whole. And then the final column is maintenance. Do we know if the lamps go through regular cleaning, including the fixture lamps? We do this before we actually go out and take lighting levels. Lighting levels should be taken with the lamps in the cleanest possible condition to get an accurate idea of the true light level in a space. Now, how many buildings actually go through and clean fixtures and lamps? Probably not very many. So I would guess when you go out and do an energy audit, most of the lamps and fixtures are in the dirty condition, or at best, we don't know. The next area down, we put the condition of the lighting control. Let me get back to that. In this case, the room has lighting control based on 1/3 of the lights for 3 switches. So they can turn on 1/3, 2/3, or 3/3 of the lights, but they are manual. Things that we would want to put in there if there's any type of automated control, either based on motion, timing, interlocked with some other device, or sometimes lights are simply hardwired on all the time for security or safety reasons. In the next section underneath this, we have other electrical devices, consuming devices, or other energy consuming devices. We typically list them, how many there are, the voltage, the amperage, the wattage, and if we can determine how often that piece of equipment is used, we usually try to put it in. Below that, we have an area where we can put what the owner is trying to let us know what the occupancy of this room is. In this case, the occupancy of this particular room varies greatly. Once a week, there's board meetings in the room with about 20 people for 3 hours. The rest of the time, it's empty. Even that's a fairly large swing. But then, twice a year, there's special events where they put over 100 people in this room. So you can see that the occupancy varies considerably for this particular space. And then finally, we try to give a description of what's happening with the HVAC. So this area happens to be served by a residential split package, and we identify what room the split package is located in, or where it's located. And then we give the unit's identifier. What specifically is that unit? In this case, it was a 1993 Bryant model, and there's the model number. On the cooling side, 5-ton, a 9 EER. On the heating side, 93,000 BTUs, 93% efficient. And the controls by a digital thermostat, no scheduling capability, currently set fan on, stat off, and the location of the thermostat. If we do have a sensor with us, we'll try to measure to get an accurate bead on what the space is currently maintaining. That's typically the raw space input. Now, other things that we try to pick up at the time, usually at the beginning we try to interview the building owner or somebody familiar with the building. We try to get a historical perspective of the building, purpose, function, whatever. In this case, the beginning of this set of information gives information given by the building executive director. So there's a basic building timeline, and then we draw, or what was drawn out was a generic area or where the building is actually located and what's surrounding the building. Pictures are always great to add into these. Eventually the document will probably contain a lot of pictures. Pictures speak volumes. Now this particular building that you guys are going to be doing again, Artworks, has been around since the late 1890s. So this building has been there for a long, long time. And it's gone through a number of changes. So real interesting building to use as an energy audit. Now, over the course of the semester, every week you're going to be working on a section that's a piece of a larger report. What we're going to do now is we're going to talk about the component parts that go into an energy audit report. So an energy audit report, the individual sections, typically there's first a title page or some sort of page, introductory page, whatever you want to call it, followed by an executive summary. The executive summary is always written last after everything is looked at. So the executive summary is meant to give the owner a quick synopsis of what's happening with the building. Now the next one, there's major areas where data was collected. So in order, we do a building description, a utility analysis, a load calculation building simulation, mechanical and control section, lighting, other electrical devices or other energy consuming devices would complete the data areas. And then under recommendations, we have O&Ms, which stands for operational and maintenance issues, and ECMs, which stands for energy conservation measures, or in some locations in the country they call them ECOs, energy conservation opportunities. Now, semester project overview. In this week's section, you'll notice that under building information, you're going to have a set of building footprints, which are on 11 by 17. Strongly suggested that you get a number of these printed out. There's a basement level, or in which case Artworks likes to call a garden level. Then there's a first floor and second floor. This week we also have a set of data collection sheets. So somebody was nice enough to go out and collect the data for this building already. So this step you're going to be able to skip. Now it's something that you already should know how to do because you did it in your HVAC451 class. In Lab 3, you will have downloaded Lab 3 form. So there's actually a lab in a form format, an Adobe form. You're going to use the project information that I just discussed, the footprints and the space input sheets to answer questions on the form. So basically you're getting familiar with the building. Once you're done, you're going to save the form, attach it back to me through the assignment drop box with the assignment. And again, this class has very regimented deadlines. They're typically 2 weeks apart. So make sure you keep track of deadlines. Real crucial doing this in the real world. This ends Lab Lecture 3. You now can proceed to Lab 3. Thank you.